Okay, my good friends, we're going to talk about this solving the vacuum disaster in space. Well, guess what? There is no vacuum in space. There never was, there never will be, because light is particles. They are not waves of nothing. They are particles. Now, although we think of the vacuum of space as being empty, it actually contains energy. This stems from the oscillation in the quantum field that makes up space. These fields correspond to quantum particles like electrons, quarks, and neutrinos. Well, I'm going to show you exactly what is in space, and they are the electrons. They're photons, they're electrons, they're dust, there's particles of every size in space. And that saturates space. So we are scrubbing through space. It is not a vacuum. All right, it ends up by saying we think it means that dark matter is due to the potential energy of the proton acting at the scale of the universe, whatever that means. It's the hidden energy. It isn't immediately available. You can't see it. It's dark matter. That's why I can show you that, and you can see it. Val Baker said their next step is to figure out exactly how dark matter fits into this. Well, I can show you how it fits in. Okay, dark matter, my claim is that dark matter is these little black balls. And they were attached to little white balls until we crushed them at our Venturi, which made the black balls separate from the white balls. And that is what the muon neutrino is the black balls. The electron neutrino were the white balls. When they crash, just like Cherenkov radiation, the white creates showers, the black does not. It just stays the same. Let me elucidate that a little more, and then we're going to go on. You're going to see this a number of times. All right, just so we can move quick. This is red pulsed laser light, not protons, laser light, the smallest particles basically that exist. That is red pulsed laser light accelerated, quite obviously, gaining enormous amounts of energy, concussing just like an explosion, quite obviously. So this is the particle that is accelerating. And that is the black and the white, and that I'm claiming the black is dark matter. It's a muon, which is attached to the white, which is the electron neutrino, and the electron neutrino creates the showers, which are these showers. Precisely what everybody's looking for. And we started with light, so we're starting with the smallest particles there are. They're starting with 100 billion particles and smashing them head on, digging through the debris, hoping to discover how it all works. That's just impossible. Okay, so what is in space? What is there in space? Is it a vacuum? No, absolutely not. And why would I say that? Well, let's just start with the fact that we have our Earth. And around our Earth, we have an atmosphere. Would you agree with that? I think you would. We have oxygen, we have nitrogen, we have hydrogen, we have all kinds of gases, carbon dioxide, and so forth. Well, what does that do? That fills up our balloon that wraps around the Earth. It's an envelope that surrounds the Earth, and it ends up being what they call the ionosphere. Way out here, right there, is the ionosphere. And it's all around the Earth. And what is ions? Ions are electrons. They're extra electrons. That's all they are. Now, electrons, I am going to say that electrons make up light. They make up photons. And electrons, as we know, are in everything there is. There's electrons in every single bit of material there is. Everything is made of electrons, which they always thought coded a nucleus. But I'm going to tell you something right now. I say that the nucleus is as well is made of electrons. You can break those nucleuses and they will throw off electrons because at a certain point they become unstable. Pew, 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 pew. They shoot off electrons. Sometimes they shoot off chunks of matter that are so devastating they will kill you because they're big chunks of matter. They're not just electrons. Now, what happens in space? We know we have the Earth, we know we have our atmosphere. Now we got to talk about in between here and the sun. Well, what does the sun do? Well, it heats up the Earth, we know that. There's no question about that. Well, how does it do that? Is it some wave that comes from and nothing happens? No, obviously not. It's particles, and those particles come from the sun, ejected from the sun violently because of their heat. And if thrown off the sun, they spin through space until they smash into our atmosphere, creating what we call light. Out here, you don't see it as light because it's not bashing into anything substantially as it is when it hits our ionosphere and our atmosphere, which is substantial. It is very substantial. When you see things come through space and they hit our atmosphere, they burn up because they are hitting into literally almost like a liquid that surrounds the Earth, and that's our atmosphere, but it's a gas to us. Now, so, this is my claim. The sun itself is ejecting particles out of its surface area here, which is 7,000 degrees. 7,000 degrees on the surface. Now, they shoot out these little bitty particles, and a lot of them get pulled back to the sun. They loop back, and they can't quite snap out of there. They just don't have enough energy, but a lot of them do. And I'll show you an eclipse of the sun, and you will see the radiation come out of there. It's absolutely phenomenal, and it fills everything in space, especially right in this region. And during the day, it just pushes those particles, which are particles, and I will show you because we did light experiments. Light is light, and if light is shown to be a particle, light is particles. If particles are particles, those particles travel from the sun to the Earth. Those particles fill the vacuum, which is not a vacuum, of space. And those particles ricochet back from the Earth, from the moon, and they re-radiate back, but they radiate back in a lower frequency. So all we can get is reddish sort of light from the moon. We don't get that intense light with all the different colors like we do from the sun, because the sun spins fast particles and it spins slower particles. But the moon only spins the slow particles. It doesn't have that really intense radiation. But throughout space, the particles are just sort of floating around or waiting to do something. If they get close enough to something that attracts them, they sort of move into that atmosphere that will attract them, and they will become part of some bigger thing called a galaxy or a solar system or whatever it is. But they will start to congeal, and things will start to come closer and closer over long periods of time, obviously. But they're spinning and they're trying to interact with each other, and they will eventually grind into each other. And grind, when I say grind, that's what causes a black hole. All of the outside matter gets white as hell, but inside is your black hole because it's pushing all the dark matter in. Now let's look at the light experiments, and it'll make it a lot more clear, I hope. Now look at this. This is the sun behind the moon. It's called an eclipse. All right, so the sun is in behind the moon. Well, look at these little red spots. These are like sunspots, and these are where there's a ton of extreme energetic reactions, and these are the poles of the sun, and this is the equators of the sun, and it is spinning just like we're spinning, and everybody's scrubbing through space, so we're all being rubbed and scrubbed, and we're reacting. Our Earth atmosphere, ionosphere, is 2,700 degrees. On our planet, it's like 100, let's say. Why is it so hot out there? Because it's scrubbing these particles that are being emitted from the sun. They're everywhere. They fill the universe, absolutely loaded. There is no vacuum in space. We're making decisions on things that they don't even understand. That light is a particle. It's not just a wave. Vacuum of space is not a vacuum. Our solar system, our sun, is scrubbing through the particles, and that is an intense form of heat. It's not necessarily strictly carbon. All this work about trying to subtract the carbon, we need to subtract the expansion of the gases. It's not necessarily just carbon. All right, so I think I've just shown that light is a particle. the sun is shooting out these particles everywhere, literally everywhere, obviously. We just saw that from the solar eclipse. Now, does that mean? It means that the vacuum of space is completely loaded with particles. Those particles are negatively charged primarily, let's say that, mostly electrons, but there's a lot of photons, which are basically neutral. They're bouncy particles. The electrons are the things that create lightning and so forth. They scrub, and the electrons collect in the outer atmosphere, and then they eventually discharge. And all over the Earth, they're discharging zillions of times a second because we're collecting all these electrons. They come down and they end up going into the Earth, and they end up shooting back around, creating our magnetic field, which tries to repel them, but they still scrub. And they are entering our atmosphere and loading our atmosphere with electrons. Now, why are we getting overheated? What's that cause? Well, just think of if we put a ton of gases in our envelope here, which I talked about being a balloon, and that balloon swells, instead of scrubbing lightly, it's pushing hard. This is not going to change how much comes at us. We're just going to push harder at it. So in other words, it's like having a tire that's this big around and sort of going, and it's not really reactive. And then all of a sudden you got a gigantic tire scrubbing. Now you got a whole different situation. And that's what's happening. That's why all this turmoil, tornadoes and water and rain and hurricanes and all this droughts and so forth, because areas on the Earth are going to, you're going to have days where you got a little more radiation, and it's going to cause heating in certain areas, and then there's going to be droughts are going to occur in certain areas where the Earth scrubs against these particles. It's a scenario that's going to get worse and worse and worse if we can't stop the envelope of gases getting bigger and bigger and bigger. And as far as I can see, we're not. And I have to tell you something right now. This is a disaster. 5G is everybody wants it because it's fast and all that. Yeah, absolutely. However, 5G is in a microwave range. Microwaves, the reason they have to put up so many towers is because they evaporate water. They literally evaporate the water that's in the air, exactly like they do in your microwave oven. If you put something in there, you're going to see steam come out of there because it's evaporating the water molecules by shaking them at the exact frequency. That is making more gases. So I don't care if you talk about CO2 or water vapor. It's the same thing. It's expanding gases. It expands 1,600 times, I think, water once you evaporate it. So is 5G a great thing? I'm not so sure. We have to look at that impact because it's going to blow up the envelope. As far as I can determine, that's almost an absolute certainty. Now, I will confess to having shown this probably close to 1,000 times on many places. However, it's still not understood that light is a particle. Nobody knows whether light is a particle or a wave or what it is. Well, I'll tell you, it's a particle and it is a wave at the same time. That's the wave, but the particle sits right here. Now, let's look at what the particle is, and let's look at the whole interaction of light coming through the air and how it manifests itself, and why I can claim it's a particle. You see, the green are the same particles. So we're dealing with light. Light is light. I don't care how you cut it. If light is light, light is light. Now, when we went further than this, the blue is just a little too intense to make out its actual physical construction like you can the red and the green. It's just, the blue is much more extreme, and it's just not easy to see. Now, these are what they call the Higgs fields, and they come after the showers. And right there, I'm going to tell you right now, I think we can get free energy right there. You could see the increase in energy is exponential. They say it's 200 times, and I can accept that, 200 times the value here compared to the value here. All we need to do, and I know exactly what needs to be done now. It's not even a hard stretch whatsoever anymore. We need transition metal thin film elements here to act as a solar collector. Not outside somewhere, inside in a controlled environment, in a shoebox basically. They would have this thin film, semiconductor, CMOS metal thin film receiving plate. And then behind that you might want to have copper or something that would keep the electrons from moving through it and drive them down into some delivery device. Now I have this pretty well laid out. And it's not a hard thing to do. It's really not at all. We're shooting electrons, and there's just nothing but electrons here. It's just like electrons coming out of a generator. And then you have to put them through rectifiers and diodes and capacitors and all that stuff, and then filter it and so forth. But then you just feed those electrons out to your house or your car or your whatever you want. And you could carry it around in your hand. I'm talking about a shoebox. You could power a house. I'm almost certain. This is raw energy, 200 times the input. And you take just a little bit of it and keep it going, make the thing keep going. You got 100 times extra. I mean, it's just phenomenal what this should be able to be done. And for the people that are running these are government agencies that are trying to help us with our energy needs, and I don't see that happen. I see them just denying to look at this. I was told we won't spend 1 minute looking at what you have to present because you're not certified and peer-reviewed and all that, so just stay away from us. And that's what I was told. I refuse to spend 1 minute looking at this. That's what I was told by Fermilab. So that's just not right. Okay, I just want you to start thinking about this 5G and the microwave frequency that it operates in and what it does, and it causes water vapor in the atmosphere. And weather satellites measure atmospheric steam, which is nothing more than water vapor. Well, there it is, or water vapor, using passive sensors. Now, they're worried about not being able to track weather correctly because we're going to be putting so much water into the air, evaporating it by 5G. Basically, that's what they're talking about. I think we should think about that a little closer. All right, this is going to get a tiny bit geeky, but this, I'm telling you right now, this could be a serious good thing for the entire world. Because if you didn't have to fight for resources and you had free energy, that's absolutely a game changer for the entire world. Now, these are the transition metals. They are in the center of the periodic chart. And what they do is they transfer the molecule of the atoms back and forth, the elements, to build molecules. Now, that's why you see all these colors. Why do you see colors? We see colors because there's different distances that these electrons are being shot out from the nucleus. So if it's a little further out, it's going to be reddish. If it's coming from the real core, it's going to be blue because it's got more energy. Now, what do we need to do to absorb all of this radiation that we just showed that the Venturi can create? Absolutely. When you see a brilliant white like that, that means you've got every color there is in extreme quantities. Well, we need to get every color back. Right now they're using titanium and in these new type of cells, but they can't really get them manufactured to go outside. I don't care about going outside. I want them inside. So I want to be able to use all of these different metals in thin film, and I'll show you exactly how this is done. It's very simple. It can be done very quickly by anybody in the world. You have your laser, pulse. You got to tune the Venturi where you get the most amount of absorption here of extreme energy, which I showed you. Now, at this point here, I'm just showing you what happens. They look flat here in the beginning, the pulses, and then they sort of tip sideways, and then they show like this, and then they shower. Now, at the shower, we need to put something like this right in here. This is the thin film. Same thing of all of these different transition metals, only just thin films of them. So when those light particles bash in there, or this extreme brilliant white, which is made up of all of these colors, we get all of these extra electrons will be able to be absorbed in here. We shoot them down into our, this is a storage device, battery basically, and then you do whatever you want with them. We're going to send them back through a load, whatever the load is, back into the other side, and that conduction will go that way. If we're flooding this so extremely, and it can absorb them, and somehow we can keep them from getting to the other side without forcing them, in other words, to go through this, just like a water hose. You have the tank, you shoot the water into here, it fills up here, and it can go into nowhere else. It's got to go through until it comes back to the other side. That's what we're trying to do. And that it's like a diode device where it can only go one direction, and then it has to come back, and it just goes around and around and around if you flood it with enough extreme energetic particles. They have to go somewhere. And I don't think this is not understood well. This is very well understood. It's nothing more than a solar panel, only we're going to be using different materials other than the silicon, basically, which is what they're using now, which is not very efficient. It's only like, I think, 20%. We should be able to achieve, I would think, almost 100%, way, way, way up there, because we're going to be able to pick up every single different light wave there is. All light waves are is colors. Colors in mass turn into white light. So I think we got a chance of, and these are not going to be exposed to the elements, so we don't have to worry about all the standards they have now for these solar panels, because the standards are absolutely phenomenal. If you look to see what these things are capable of withstanding, I think there's a 25-year guarantee on them that they'll withstand, and they have to take hail and all kinds of things. So this will be inside of a shoebox, creating energy, and you just plug into it. So somebody's got to have to do this. I hope somebody will.